Okay, let's continue. The last time we talked about the regression analysis. Okay, compared to the interpolation function in the interpolation problems. Okay, if we use the interpolation method, the solved approximate functions will pass through all the data points, and that's the interpolation functions. But if we use the regression analysis, the approximate functions will not pass through all the data. So the approximate functions will not pass through all the data. Therefore, we have the error for each data point. So we have the error for each data point, and the standard of the solution for the approximate functions, we need to if we got totally we got n data points, and the standard of the regression analysis, the approximate line should give you the minimum of the S. Okay. Okay, so the purpose of the approximate line, it should give you the minimum of the capital S. So the regression analysis, or sometimes it is also called the least square analysis. Okay, so the least square of the errors. So the most important thing you need to understand the definition of the capital S, which is the summations of the squares of the errors. Okay, you can print the screen since I like to erase the. Okay. Okay, last time we assumed okay, most of the time we use the polynomial function, since the polynomial functions, which is the one we are familiar with, and also the polynomial functions, it is easy to calculate the derivatives, or if sometimes we like to calculate the integrations. The polynomial functions, it is very easy to do all of these. Okay, so we will assume the g of x which is the okay, so the highest degree of the polynomial function, which is m. So that's the mth degree polynomial functions. And if we assume g of x, which is the mth degree polynomial functions, totally we got n plus 1 unknowns. So there are n plus 1 unknowns. Okay, so that's the assumed functions, and we can take the partial derivatives, and we know the capital S is equal to the summations of fi minus okay, so and the m should be less than n minus 1. Okay, and the number of the data points should be greater than n plus 1. Okay, in this since the regression analysis it is only approximate functions. Sometimes the interpolation functions it is also the approximate function, since the original function f of x, which is not only the polynomial functions, sometimes it is a very complicated functions f of x. But no matter the interpolation method or the regression analysis, we always use the polynomial functions. So both methods, they can give you only the approximate functions. The difference between these two methods, one of the method, the interpolation functions, it will pass through all the data points. But if we use the regression analysis, the approximate functions will not pass through all the data. Okay, so that's the definitions of the error. So in the outside parentheses, which is the calculations of the EI, okay, the Fi is the function value at the data points, and the Fi, they are the input data. Whenever the user likes to do a regression analysis, he needs to input all the xi and the fi. Xi is the value of the parameter. The fi is the corresponding function value at these data points. And the inside parentheses, which is the function value obtained from the g of x. Okay, so the fi minus g of xi, it is the e of xi. Okay, and the definition of the capital S, we need to calculate the error at each data point, and also we need to make a square to calculate the square of the error. And if we calculate the square of the error, so it means no matter the error which is positive or negative, okay, no matter the fi is larger than the estimated value, or the fi is less than the estimated error, estimated value, and they both of the positive and the negative values of the EI, it will contribute to the capital S. Okay, so the square will make the positive values or the negative values, they will all contribute to the capital S. Okay, so we the obtained g of x functions, usually it will be an approximate line, usually it will go close to the middle of the scattered data points. It will not always on the top, or it will not always on the bottom, close to the bottom of the data points. Usually it will close to the middle values of the data points. Okay, so the first method, how can we solve the g of x? We have the defined capital S, and totally we got n plus 1 unknowns. They are the A0, A1 until the AN. And we like to control all these unknowns to make the capital S, which is a minimum value. And for the minimum value, we can use calculate the partial derivative of the capital S to the first unknown A0. But if we like to get a true minimum, not only a locally minimum, then we need to calculate not only to the first unknown, the partial derivative should be equal to zeros. Also, we need to check the second equations, partial A1, partial capital S to 0, until the last one, partial AN, partial capital S equal to 0. Okay, so totally we can get n plus 1 equations. And from these n plus 1 equations, we can solve all the n plus 1 unknowns. Okay, so that's the first method. How can we determine these approximate functions? Okay, you can print the screen, and I will erase it. Okay, the second derivation method, which is I like to emphasize, since the second derivation method, I will use the matrix form to derive the methods which can help us to solve all the unknowns. Okay, so if we say the EI is equal to Fi minus g of xi, okay, and then we can define an error vector which include the error for all data points. Okay, so it is a vector, E vector, and for this E vector, it includes n elements, the E1, E2 until the En, and they are the error for all the n data points. So the E vector, which will be equal to the F1, F2 until the Fn minus 1. Okay, so the first vector, they are the F vector. For this vector, it includes the function values for all the n data points, and it is the second matrix. We can say that that's the B matrix. Okay, the B matrix, we can always calculate all the elements in this B matrix. Since remember the F vector and all the x1, x2 until the xn, they are the input data for this program. And also remember that we cannot have the duplicated xi values. All the xi values, they should be different. Okay, so since the user needs to input all the xi and the fi, so if we know the x1, x2 until the last xn, then we can always calculate the B matrix. Under the A vector, which includes all the unknown coefficients for the approximate function g of x, under the A vector, which is the basic unknowns of this method, if we can solve all the A0, A1, if we can solve all elements in the A vector, then we can say we have already solved the approximate function g of x. Okay, so it is a matrix form of the air functions. And what is the capital S? Capital S, which is equal to summations of EI squared. For this one, we can say which is the E vector transpose E. Okay, so we can use the basic calculations for the matrix, and if we have defined the E vector, then what is the capital S, the summation of the EI squared? We can use the E vector transpose multiplied by the E vector. Okay, so if we multiply these two matrices together, then you will get the same results, which is the E1 squared plus E2 squared until the last term, the En squared. Okay, so we can use the E transpose times E vector to get the capital S. Okay, so that's the you can say that's the matrix form of the definition of the capital S. Okay, you can print the screen, then I will continue. Okay, we can replace in the last screen the E vector, which is equal to the F vector minus B times A, and we need to transpose the first for the E vector multiplied by the original E vector. If we can multiply these two together, then we can get the capital S. And how do we calculate the transpose of this one? And which is equal to the F transpose minus A transpose and B transpose times F minus B times A. Okay, so if we multiply these two together, we will get Okay, so that's if we multiply these two terms together, then we can get the totally the 4 terms. And how can we get the A vector which can make the capital S which can make the capital S an extreme value, and the extreme value, it should be the minimum value. Okay, so the purpose of our derivations, we like to get the A vector which can give the minimum capital S. Okay, so but right now, if we use the matrix form to calculate the capital S, it is not, usually we will not take the partial derivatives for all the unknowns A0, A1 until AN. We will use the variation method, and we will make the variations take variation for capital S. Okay, how do we make a variation of the capital S? First, the variation means that we will vary anything which can be varied. Okay, we will make a small variation. First, we will the concept of the variation method. We will change the values for everything which can be changed. Okay, so we will check. We will check the target function capital S, and let's check which one it can be changed. And if we check the target, the capital S, you will find we cannot change anything in the F vector, and also we cannot change anything in the B matrix. Okay, so the F transpose F, and for these parts, everything in the red circles. Okay, for everything in the red circles, we cannot make any change. Since remember the xi and the fi, all the xi and the fi, they are the input data from the program user. So we cannot change anything in the B matrix. Also, we cannot change anything in the F vector. Okay, in this problem, the only thing we can change, they are the elements in the A vector. And no matter the A0, A1 until the last coefficient AN, all the coefficients for the g of x functions. Since right now we don't know what g of x functions we can get, and we just assume the g of x functions, which is m minus 1th, polynomial functions. Okay, so if we assume the g of x, which is m minus 1th degree polynomial functions, then we do not fix the target functions. So all elements in the A vector, they can be changed. And the variation method, we will make a small variations for anything which can be changed, and the elements, they are the A vector. All elements in the A vector. Okay, remember the all elements in the A vector, they are the control parameters for these problems, and all the coefficients, they can be changed. Okay, print the screen. Then I will erase it. Okay, so how do we calculate the delta S? The delta S is, so it means that we will make variation. We will make variation for the capital S, and remember they are the S of A. Okay, so that's the delta S. Remember, first we need to check anything in the capital S, which values it can be varied. Then we just make then we will just make variations for all these parameters. And in the regression analysis problem, we found only the elements in the A vectors, they can be changed. Okay, so if we make variation about the capital S, so we will make a delta A vector, and all elements in the delta A vector, the delta A vector, we will make an arbitrary and small variations of this element. So the delta A1, which is an arbitrary and okay, so the delta A0, which is an arbitrary, and also it is a very small variation for A1. Okay, so that's we can make an arbitrary and a small variation for the A0, and these small variations is defined or it is termed as the delta A0. And also we will make a small and arbitrary variation for the A1. Then it is the delta A1. Okay, until the last term, the delta AM. It is also an arbitrary, and also it is very small variations for the last coefficient AM. Okay, so all these variations, they are just random, and all the data values, they are independent. So you can make positive variations for the first element, and but for the second element, it is a negative small variation for the second element, and also the magnitude of the variations, they no need to be very close. So you can make 0.1 for the data A0, and the negative 0.001 for the next for the second element data A1. You can make any kind of the small variations for all elements. Okay, that's the ways we make the variations of this one. Okay, so how can we find the point of the A vector? Where is the target? Where is the target of the A vector? Okay, which point or where is the A0, A1, and the AM of our target? Okay, so if the A vector which will give you the minimum capital S, okay, our target is find the A vector, and the vector will give you the minimum capital S. That's our target. That's our target. And if the A vector is the target, then you can say, no matter what kind of the very small variations of the data A, the results is always equal to 0. Okay, so first you need to understand if the A vector, which is corresponding to the minimum of the capital S, then any small variations of the A vector, the difference between these two, they are close to 0. So it is the bottom point of a value. So if you make any small changes, the capital S, the difference between the capital S, it will always equal to 0. Okay, so that's the criterion to give you the minimum capital S. Okay, it's time for you to print the screen. Then I will continue to calculate the variation of the A. Okay, so that's the capital S. That's the capital S. Also, we can prove these two terms, they are same. We can prove these two terms, they are same. First, all these two terms, they are the scalar. The scalar means the result of this one, which is a 1 by 1 matrix. This one is also 1 by 1 matrix. Okay. All these two they are the 1 by 1 matrix. And for any 1 by 1 matrix, for any 1 by 1 matrix, we can always, they are always equal to the transpose of it itself. Since it is a one row and one column, if we make a transpose, the first row will become the first column. And but right now the first row is we got only one element, and it makes one column, so it is always the same. So for the if the 1 by 1 matrix, if the transpose if we got the two matrix, C matrix and the D matrix, and if we can prove the C is equal to the D transpose, then C must be equal to D. Okay, for the 1 by 1 matrix, if it is equal to the transpose of it itself, then we can prove these two matrices, they must be same. They must be same. Okay, and then that's what we like to prove. For the transpose of the first one will be same as the second one. And how do we calculate the transpose of the second one? If we make a transpose of the second term, it will be the A transpose, B transpose, and the F. So it is the same. So these two, they are the same. These two, they are same. These two, they are same. They are same. So you can change we can rewrite the capital S. Okay. Remember, since these two terms, they are same, and the C matrix is equal to the D matrix, And so we can use if we like to calculate the C plus D, since the C is equal to the D transpose, then we know the C matrix is always equal to the D matrix. If the C is equal to the D matrix, then C plus D matrix, it will be the twice of the C matrix or twice of the D matrix. We can use either one. And right now I choose the third term to make it is a double. Okay, so this one is capital S. This one is also capital S, but we can always combine the second term and the third term to use this one. Okay, I think I will take a break, although it is only for the 45 minutes, but I think it is a good time to take a break. Okay.